So we are back again. Today we will be solving the Leetcode Biweekly Contest 83. I attempted the contest and managed to get a rank of 345. Although this is not my best, but yeah, whatever. So let's dive into the problems. So the first problem, best poker hand. So here in this problem, we will be given two arrays, ranks and suits, each having length of 5. And we need to return a string based on certain conditions. If all of the values of the suits array are same, we need to return flush. If the at most, at least 3 cards have the same rank, then we need to return 3 of kind. If 2 cards have the same rank, then we need to return pair, else high card. So it's a very straightforward question. Let's straightly dive right into the code. So first of all, we need to count how many occurrences are there of the any suit. If it's equal to 5, then we directly return flush. Else, we would be needing the maximum count of any two pair of ranks, any occurrence of ranks in the ranks array. So we just run a n squared loop and get the maximum count. And if the maximum count is 3, we return 3 of a kind. If maximum count is greater than equal to 2, we return pair, else return high card. Since the length of the both the suits and the ranks array are very small, that is 5, so the time complexity is big of 1 basically. Only this takes big of n square, but n here is 5, so it will be 25 steps. Okay, let's dive into the next problem. Number of zero-filled subarrays. It's a very straightforward question again. We are given an array and we need to return the number of subarrays which have only 0 values in them. So what we can do is we can, let's draw this. Yeah. So let's say we are given 1, then 2, then 0, then 0, then 3, then 4, then again some 3 zeros as dot dot dot. So we can iterate from the beginning, and as soon as we encounter a 0, we start a loop from there and continue as long as we find all the zeros. So this is a continuous group of zeros that we get. So as soon as we get a subarray that is continuously filled with zeros, we need to find how many subarrays can this degenerate to. It can comprise of this single zero, and this as a whole. This is nothing but if the length of the subarray is n, it will be n into n plus 1 by 2. So it's again a very straightforward question. Let's see the code. So here I'm creating a variable named index, which denotes what is the current point that I'm standing. And if the value of that particular index is not 0, we just increment the index and move ahead. And if we encounter a 0, I create a variable count, which stores the count of contiguous zeros that I found till now, and iterate the temporary pointer j and increment the count. After we have got all the consecutive zeros, we increment our answer with count into count plus 1 by 2 and move our current index pointer to j. And finally, we return our answer. So the third problem, design a number container system. So here we will be given two type of operations and we need to design that. First operation is we insert or replace a number at any given index, and the second operation is we need to return the smallest index for the given number in the system. Okay, so we can do here is, yeah, first of all, let's focus on the first operation, insert or replace a number in the system. Let's try to think what all data structures do we need to solve this problem. The first data structure which is clear is we need to create a mapping of any number to all the corresponding index that it is present at. So let's say the value 2 is present at index 3, 4, and 5. So whenever the operation 2 comes, we need to return 3. Operation 2, return 3. So it clearly shows that we would be needing some sort of mapping which maps an integer to a set of or a vector of indices. And we would always need that vector to be sorted because we would be needing the minimum element. So the best case scenario would be we can create a map of integer to a set of integers which stores all the occurrences of that particular number. Now let's focus on the first operation. The first operation is of inserting or replacing a current number at a given index in the system. So let's focus on first operation, and within first operation, let's focus on the insert operation. So when we will consider that, be sure that the current operation is a insert operation and not a replace operation. If and only if we don't have any index in which the operation is called, because the first operation we will be given an index and a value. So if index, if we are encountering the value index for the first time, that means we are getting a new insert operation. So we can store some sort of mapping that what this particular index stores. We can see here of current value. So what is the current value at that particular index? This map will store this. So whenever we get an insert operation, how do we determine if it's an insert or replace operation? We can check if current value map, if current value contains the key index. If it doesn't contain, if key is not found, that means it's an insert operation. Else it's a replace operation. So if we get an insert operation, it's very straightforward. What we can do is we can do current value of index and we can do value, which means that at the position index, we have got a new value there, which is of value. And also, since we have got a new value, we can update its occurrence of value, and we will insert the particular index there. Now, what if it's a replace operation? So if it's a replace operation, there was a previous value at that particular index, which will now be replaced. So let's get what was the previous value. Previous value would be nothing but the current value of index before updating the map. Since this is the previous value, we need to update the occurrence. That means we need to delete the value of index from its occurrence, because the previous value will be no longer be at the position index. So what we can do is we can erase the value of index from its occurrences. And after erasing, it might happen that there are no more occurrences of previous value in the occurrences map. So we can check if size of occurrence of previous value is equal to 0. That means there are no more occurrences of this particular value. So we can directly erase this key from the occurrences map. Now that we have erased it, we can update our current value of index to be value, just like we did in the insert operation. And we can do the current value of value dot insert to be index. So yeah, this is it. So we can see here in the change operation, that is the first operation, we check if the current value dot find index is not pointing towards to the end of the map. That means if the key is present or not. If it's not present, that means we just it's an insert operation. It's an insert operation. And if it's present, it means and it's an replace operation. So we get the previous value, we delete the occurrence of index from the previous value, and then we check if the size of occurrence of previous value has become 0. Then we delete the key of previous value from the occurrences map, and then we update it. And whenever we get the second operation of getting a smallest index in which the number occurs, we just check if in the map we have the index, we have the key of number. If it's not, that means there is no such index which contains this value of number. So we just return -1. Else we get the smallest element, which is the star begin function of the C++ STL. And then we just return the index. Better name it as index. Yeah, that's all. Moving on to the last and the hard question: shortest impossible sequence of rows. So we'll be given an array of length n, which is called here roles, and we'll be given another integer k. The basically k here denotes that we have a dice of side k. So any dice will be having all the values from 1 up till k, and if we roll the dice n times, then we uh, get all possible sequences from 1 up till k. So the result of the ith roll of the die is given as rolls of I. So we need to return the shortest sequence of rolls that cannot be taken from rolls. So since the problem statement is a bit complex, let's dive into the example. So here we were given the array rolls, and we are given a k value of 4. So every length sequences are generated. So for length 1, what all sequences up from we can have? We can have a 1, 2, 3, and 4. All these sequences are present in this array. Let's take a length of 2. What all sequences are there? 1, 1. 1, 1 is also present. 1, 2 is present. 1, 3 is present. 1, 4 is present. Similarly, 2, 1, 2, 2, 2, 3, 2, 4. So every sequence up till 4, 4 is also present. So we get every sequence of length 2. Now let's try to check if we have every sequence of length 3. We can clearly see that the occurrence of 1 in the entire array is 2. So we can definitely not get a 1, 1, 1 as a subsequence in this array. So the answer will be definitely 3. Okay. So this problem is quite easy if we can observe a small thing. How can we check if all sequences, check if all sequences, or let's call all permutations where each index can have values from 1 to k is present or not. Permutations of a given length is present or not as a subsequence. If we find the smallest length such that all the permutations are not possible to generate, that will be our answer. Let's say I make a claim that all permutations of length x is possible. That means 1 till x, 1, 2, 3 up till x, 1, 3, 2 up till x, and so on. 4 up till x, x minus 1, 1, and all. Every permutation of length x is possible. Now we need to check if x plus 1 is possible or not. How to check if x plus 1 is possible or not? Since we know that all the permutation of length x is possible, to make the length or all the permutation of length x plus 1 possible, what we need to do is we need another set of 1 up till x after the last index at which all the permutations of length x got discovered. So let me make this statement a bit clear. We want to get all the permutations of length x at the smallest possible index, and at the smallest possible index. What do I mean by here? This statement is, let's take the example of this array. Let's copy this, paste it here. Yeah. So in this possible, let's increment the size up till 20. Yeah. So in this possible sequence, I want to make a claim. Check if every permutation of length 1 is possible or not, and not only check, find the smallest index till which we need to consider as a ending index. Basically find the smallest index from the prefix such that we get every possible sequence of length 1. So every possible permutation of length 1 would be 1, 2, 3, and 4. So this is the smallest possible subarray that contains all the permutation of length 1 to 4, of length 1 having the values 1, 2, and 3, and 4. Now if we need to extend it for length 2, what we need to do is we need to check after this and do the same operation, find the smallest possible index where we get all the occurrences from 1 till k, starting from the index, the very next index, which the previous operation just ended. By this, I mean that for length 1, we took this subarray, right? So for length 2, we need to start from the just next index, that is this index, which my cursor is currently pointing at. From this, we need to go on up till we find every occurrences of length k, of every occurrences of values from 1 till up till k. So this is the last index which we get all the occurrences of 1, 2, and 3 and 4. So this means, since we have got all the occurrences, this means that we can get a permutation of length 2 as well. Now, if we were to check for permutation of length 3, since we ended at the very last index, there is no space for us to explore the permutations or the next occurrences of 1 till k. Had the array been 1, 2, 3, and 4, then we would have gotten all the permutations of length 3 as well, because for length 2, this is the smallest index using which we can generate every possible permutations of length 2. So for length 3, we need to start from this index and go on up till the end and find the smallest index, which contains all the occurrences of length of values from 1 till k. Since this also contains the values from 1 to k, we get the we can definitely generate all the permutations of length 3 as well. So the idea is very clear. Iterate from the beginning. Iterate. I'll be writing the algorithm now. Iterate from the beginning. First of all, initialize our target length. Initialize the target length, which denotes the smallest possible length whose permutations can't be generated. So initially, we initialize it by 1. Then iterate from the beginning of the array and keep a track of all the occurrences of values from 1 up to k. As soon as we get all the, as soon as we have seen all the values from 1 till k, clear the frequency map and increment our target length, because we have got the, we can definitely say that the previous target length can be achieved. So we just increment it. So this is a simple algo. Let's see the code. The code is very short. We keep an index which denotes the current position of the array that I'm currently present at, and we also store the array size. And current length or our target length is initialized as 1, and we store up frame map of frequency, which will store the frequency of all the values from 1 till k. Then we iterate from the beginning and we increment the frequency of the particular value of that at that particular index. So as soon as we have seen all the values from 1 till k, we clear the frequency map and we increment our target length. So the final value of target length would be the one having the smallest length whose all permutations can't be generated. So that was it for today. Hope you liked it. If you have any doubts, do comment. And that's all. Thank you.